Hi, my name is Mark Ronnenberg from Indiana University, and today I'll be talking about a prequantum bundle on the traceless character variety of a surface with boundary. So I'll tell you a little bit about what the prequantum bundle is, what's a traceless character variety for a surface with boundary, and also what's a traceless character variety for the complement of a tangle in a three-manifold, and sort of how all of these relate to each other. So a tangle in a three-manifold is just a properly embedded one-dimensional submanifold. There below, you can see a picture of such a thing. In black is the tangle, and in gray is the boundary of the three-manifold. If I remove a tubular neighborhood of a tangle, then I'm left with a new three-manifold whose boundary consists of a surface with boundary along with a disjoint union of annuli. So here's a picture of such a thing. In green are the annuli. Those embedded annuli are supposed to be remembering where the tubular neighborhood of the tangle was. And if I were to remove those annuli, I'd be left with a surface with boundary. Now, to a surface with boundary, I can associate something called the traceless character variety, defined as follows. I consider a trivial principal SU2 bundle P over R surface F. The space of connections on P can be identified with the space of SU2 valued 1 forms over F. And then I can define the traceless character variety as follows. For a space of connections, we'll take all flat connections that restrict to be I over 4 d theta at the boundary of F. That choice of I over 4 guarantees that we get traceless holonomy around the boundary components. And then for our group of gauge transformations, we're going to take all maps from F into SU2 that restrict to be a constant element of U1 as a subgroup of SU2 at each boundary component of F. And we just know you could get a different constant at each boundary component. Now, this gauge group acts on that space of connections. And so to define our traceless character variety, we'll just take the orbit space of that action. And it's a well-known fact, going back to people like Atiyah Bott and Goldman, et cetera, that this is, roughly speaking, a symplectic manifold. Over a symplectic manifold, I can construct something called a prequantum bundle. For us, that's just going to be a principal U1 bundle over our symplectic manifold, equipped with a connection whose curvature 2 form is a multiple of the symplectic form. In a minute, I'll tell you how to construct this over a symplectic, over the traceless character variety of a surface with boundary. First, just mention that there is a traceless character variety for the complement of a tangle as well. If we let V denote the annuli embedded in the boundary of the tangle complement, then we can define the traceless character variety as follows. For a space of connections, we'll just take all the flat connections that restrict over F to be traceless. In particular, they should have traceless holonomy around the meridians of each annulus. And then for our gauge group, we'll just take all the mass from Y into SU2 that restrict to be a constant element of U1 along each annulus. Again, it could be a different constant on each annulus. Again, this group of gauge transformations acts on that space of connections, and the orbit space is what we will take to be the traceless character variety. There is a natural restriction map from the traceless character variety of tangle complements into the traceless character variety of the surface with boundary, and under favorable circumstances, that is even a Lagrangian immersion. Now, for a three-manifold, there's something called a Cher-Simons function, which acts on connections by the formula shown on the screen. This is well-defined modulo Z up to gauge equivalence, so long as Y is a closed three-manifold. But if Y has boundary, then that's no longer true. This is not well-defined, and so it's not really a function. But we will be able to view it maybe as a section of a certain bundle, our prequantum bundle, which we are about to define. So to construct our prequantum bundle following Ramana, Singer, and Weitzman, we will do as follows. We will define a map theta from connections over the surface of boundary times gauge transformations over the surface of boundary into U1 as follows. We take a connection A, we take a gauge transformation U. We choose any tangle complement whose boundary is our surface union a bunch of annuli. We choose any extensions of A and U over Y. And then we just define theta AU to be e to the 2 pi I times 8 times an integer times the difference Cher-Simons evaluated on extension of U times extension of A minus Cher-Simons evaluated on extension of A. That weird choice of 8 times an integer ensures that this theta is a well-defined function. And now we can make the gauge group act on the trivial U1 bundle over connections via the formula on the screen using theta. And then we define the bundle to be the orbit space of that action. And finally, we point out that we can now actually view our Cher-Simons function for the three-manifold as a lift of that natural restriction map, which basically allows us to view it as a section of that pre-quantum bundle as indicated by the diagram on the screen.